Hi everyone. Well, in section 1.1 of Math 1001, we made a good start on this topic of indefinite integration. And in particular, we saw how we can take a lot of our results from differentiation and basically turn them around, sometimes with a little bit of extra work, and turn them into results that will allow us to evaluate elementary indefinite integrals. But what we also discovered is that whereas integrals of sums and integrals of differences and integrals of constant multiples all have properties that basically correspond with the same properties that we know from differentiation, there's nothing that corresponds to the product rule or the quotient rule or the chain rule. So in other words, in general, integrals of products, integrals of quotients, integrals of composite functions, they pose a really big challenge. There are exceptions. For example, we figured out how to deal with the case of linear composition, but that's far more the exception than the rule. And so we need to figure out new tactics, new strategies, new techniques to handle non-elementary integrals in general. And that's where we're going to start here in section 1.2, where we're going to introduce the first of these more sophisticated methods, which is known as integration by substitution. But before we can get into that topic, we need to go back to the way we represent integrals and investigate that a little bit more. And in particular, this differential, the dx or d whatever the variable is, that we've been putting at the end of the integral. That's worth looking at in a little bit more detail. When I introduced it in section 1.1, I made reference to the fact that this has its analog in the Leibniz notation for differentiation, where we would represent a derivative as d over dx. So there's a certain consistency here, but still, that's got to mean something. That's got to be present in the integral notation for a reason. And to start, let's actually go back beyond calculus to pre-calculus and our study of things like lines. So let's consider a line, let's just call it L in general. Its slope. We know that that's given by, we call it m. Well, that's the change in the y-coordinates divided by the corresponding change in the x-coordinates. So delta x here, and I know I'm probably telling you something you already know, but it's good to remind ourselves of these things occasionally. This is going to lead somewhere momentarily. So delta x here, that represents the change in the x-coordinate. And delta y, that represents the corresponding change in the y-coordinate. Okay. Well, in Math 1000, we specifically looked at the case of the tangent line. So this formula applies to any line at all, but in the case of a tangent line, we've got a little bit more information about the slope. So now let's suppose that this line L is the tangent line to a curve, let's say generated by a function y equals f of x, could be any function, at a point x. Then we know that the slope at that point is given by f prime of x. So that means that delta y over delta x is equal to f prime of x. And I could take that then, and I could rearrange it. And that would tell me that the change in y is going to be given by the value of the derivative at that point multiplied by that corresponding change in x. But we've got to be a little bit careful here, because remember that the tangent line, that's only valid at a specific point. And so, in general, while this is going to be a true statement for the tangent line, that the change in the y-coordinate along the tangent line is always going to be equal to the value of this derivative times the corresponding change in the x-coordinate, we can't take that formula and generalize that to the curve y equals f of x itself. Because unless that curve is a line, well, that derivative is going to change as we move to different points, to different values of x on the line. And that's part of the intent behind the Leibniz notation, which of course I could use here instead. I could write this as delta y equals dy by dx times delta x. Because that's also a way of describing a change in y relative to a change in x. But the reason we use the d there, that differential operator, is to denote not just a change, but a very, very tiny change. In fact, when Newton was developing calculus back in the 17th century, he described it as the study of infinitesimals. So this is really meant to illustrate the infinitesimal change in y that results from an infinitesimal change in x. So, well, could we then adapt this formula? Well, the delta notation, in general, that's meant to represent a substantial change, a large change, relatively speaking, in the variables. So we typically use delta x and delta y to represent a large change in the variable. To indicate an infinitesimal change, we instead represent this as dx or dy, and exactly as we introduced in the last section, we refer to these as differentials. So therefore, if a large change in y can be written as the derivative times a large change in x, then it's very natural to conclude that a very infinitesimal change in y, so in other words, the differential for y, must therefore be equal to the derivative times the differential for x. So in other words, dy is equal to dy by dx times dx, which kind of puts the lie to something you may have been told in Math 1000. When Leibniz notation was first introduced, you were probably told that dy by dx, that's a single entity, that you can't treat it like a fraction and break it apart. And in principle, that is true. If we're representing a derivative, dy by dx is a single thing. It stays together. It's all basically one slightly complicated symbol to represent the derivative, the same way f prime of x is. But now that we've introduced the differentials, because we've got this relationship between two differentials and the corresponding derivative, it means that for all intents and purposes, we really can treat that Leibniz notation for the derivative as if it can be split apart, because this looks as if the dx's here are being canceled to give us the dy. That's not actually what's happening, but we can essentially interpret it as if it were. Now, how is that going to be helpful to us here in the study of integration? Well, as we've seen, the differential is present in our integral notation. And the reason for that, the real reason for that, we're going to have to leave that until Unit 2, when we get into the idea of definite integration. That's where the presence of that differential will really get justified. So you'll have to bear with us a little bit here. But in particular then, what this tells us is that if we have an integral done with respect to one variable, the variable that's present in the function, suppose we realized that that integration would work much more easily if we were working in a different variable. Well, the core problem with that is that the original variable pops up in the differential as well as in the function itself. But what this relationship tells us is how we would make that change. So this lets us rewrite an integral given with respect to one variable in terms of a different variable because it shows us how to rewrite the differential. So we could go from an integral of some function of x with respect to x, so in other words, the integral of some function of x dx, to an integral of some function of t dt, or an integral of some function of theta d theta, or what we're going to see most often in this section, the integral of some function of u du. Because this method of integration by substitution that we're going to introduce, it's often known more informally as u substitution. But what is this method? How would this work? How would we know to rewrite an integral in terms of a different variable? Where would that different variable come from? Let's pick up on that in the next video.